Imagine looking up at the night sky, a canvas of infinite possibilities. For millennia, across civilizations and cultures, we've gazed upwards and wondered, are we truly alone in this vast cosmic ocean? Is Earth a singular miracle, a cosmic accident, or are there other worlds out there teeming with the potential for life, waiting to be discovered? Now, for the first time in human history, we have the tools to begin to find an answer. And the first message we've received isn't of radio waves or coded signals, but something far more fundamental, a message not of words, but of molecules. The James Webb Space Telescope, a marvel of engineering floating 1,000,000 miles from Earth, far beyond the reach of our atmosphere, has captured a faint but unmistakable signature, the presence of water vapor on a distant planet. Webb, with its revolutionary infrared eyes, pointed its golden mirror at a star located in the constellation Phoenix, a celestial bird rising from the ashes, patiently waiting for a planet, a hot gas giant designated WASP 96b, to pass directly in front of its host star. As the planet transited, a tiny sliver of starlight, like a cosmic key, filtered through the outermost layers of its atmosphere. And within that light, Webb found the unmistakable fingerprint, the telltale sign of water. Water, the same life-giving substance that fills our oceans, nourishes our planet, and flows through our very veins, exists in the atmosphere of a gas giant, a world vastly different from our own, hundreds of light years away. This isn't a fleeting glimpse, a hopeful guess, or a statistical probability. It's scientific certainty, irrefutable evidence written in the universal language of light itself. The discovery was more than just a data point, it was a turning point, a paradigm shift in our cosmic journey of understanding. Years of meticulous planning, countless hours of engineering, and the sheer ambition of building Webb all came down to a single graph, a visual representation of discovery. A clear and distinct peak in the spectrum, precisely where the signature of water vapor should be, confirming its presence beyond any doubt. It was a message in a bottle, sent from a distant shore, finally reaching us across the vast and mysterious cosmic ocean. This groundbreaking discovery doesn't just tell us about the composition of one faraway planet, WASP 96b. It strongly suggests that the fundamental ingredients for life, like water, are surprisingly common throughout our galaxy and beyond. The universe is revealing itself to be far more complex, far more interconnected, and far more hopeful than we ever dared to imagine. The apparent silence of the night sky is not an emptiness, but a vibrant chorus of unseen worlds, each with its own unique story waiting to be told. For the dedicated scientists who pored over the data, witnessing this discovery firsthand, it was a moment of pure, unadulterated awe and wonder. We are only just beginning to learn the intricate art of how to truly listen to the universe's deepest secrets, whispered across billions of miles. The search for life beyond Earth has definitively entered a bold and exciting new era, filled with unprecedented possibilities. How do we know what a planet's air is made of? How can we possibly determine the atmospheric composition of a world so incredibly far away? Especially when it's 1,000 light-years away, a distance so vast it's almost incomprehensible. It seems like an impossible task, doesn't it? The answer lies in a powerful technique called spectroscopy, and a telescope specifically built to master it, the James Webb Space Telescope. This incredible instrument is our eye on the distant universe. Unlike traditional telescopes, Webb doesn't primarily see visible light. Instead, it's exquisitely tuned to the infrared portion of the electromagnetic spectrum, the glow of heat emanating from celestial objects, revealing hidden chemical signatures within these distant atmospheres. To find water on the exoplanet WASP 96b, a hot gas giant orbiting a distant star, Webb employed a clever technique called transit spectroscopy. It's essentially a cosmic stakeout, patiently waiting for a specific event to occur. Scientists meticulously waited for the exoplanet to transit or cross in front of its host star, dimming the star's light by just a tiny measurable amount. This dimming allowed a fraction of the starlight to filter through the outermost layers of the planet's atmosphere. And that's precisely when Webb's incredibly sensitive instruments sprang into action, capturing and analyzing the filtered starlight. The key is that each type of molecule present in the atmosphere absorbs very specific wavelengths of light, leaving behind a unique pattern, a spectral barcode, which acts as a distinct chemical fingerprint for that molecule. So, by carefully analyzing which colors or wavelengths are missing from the starlight, scientists can definitively identify the specific molecules that are present in the exoplanet's atmosphere. It's a form of cosmic forensics, meticulously reconstructing the scene and the atmospheric composition from trillions of miles away. When the James Webb Space Telescope turned its gaze towards WASP 96b, it detected the unmistakable fingerprint of water vapor in its atmosphere. The data obtained was remarkably precise and detailed, providing what felt like reading a complete chemical inventory of the exoplanet's atmosphere for a distant world that we may never be able to physically touch or visit. This groundbreaking technique is completely revolutionizing our understanding of the atmospheres of distant exoplanets. We're moving beyond simply finding planets orbiting distant stars. We're actually beginning to truly know them, to understand their composition and their potential habitability. The universe is slowly but surely revealing its deepest secrets to us, one carefully analyzed spectrum at a time. Webb's data was more than a simple yes or no for water. The spectrum revealed clouds and haze in WASP 96b's atmosphere, muting the water signature. This means the planet has weather, dynamic, changing conditions. Webb doesn't just find chemicals, it paints a picture of physical conditions on these worlds. The shape of the water signature tells us about temperature and pressure. Clouds hint at condensation and atmospheric processes. We're moving from cataloging planets to understanding them as unique worlds. The spectrum also hints at other molecules, possibly methane or carbon dioxide. Finding both water and carbon would mean the building blocks for life are present. This is just the beginning. Webb is now studying other worlds, including Earth-sized planets in the TRAPPIST-1 system. Each observation brings us closer to understanding the diversity of worlds in our galaxy. Why is finding water so electrifying? Because on Earth, wherever there's water, there's life. Water is the universal solvent, the medium for life's chemistry. Its unique properties, polarity, ability to dissolve substances, and existing as solid, liquid, and gas, make it essential for biology. Ice floats, insulating life below. Water's liquid range allows stable environments for evolution. So when we search for life, we follow the water. Finding water vapor on WASP 96b proves this ingredient isn't unique to our solar system. It's being delivered to planets across the galaxy. WASP 96b isn't habitable, but its watery atmosphere is proof of concept. Planets form in water-rich environments. Our search for a habitable Earth-like world is not a fool's errand. It's a real, achievable goal. What kind of world is WASP 96b? It's about 1,150 light-years away, in the constellation Phoenix. The light Webb captured began its journey during the Viking Age. WASP 96b is a hot Jupiter, a gas giant, half Jupiter's mass but over 20% larger in diameter, making it puffy and low density. If you could find a bathtub big enough, it would float. Its orbit is dramatic, just 3.4 days around its sun-like star, much closer than Mercury is to our sun. One side faces perpetual day, the other eternal night. Temperatures soar above 1,800 degrees Fahrenheit. Its star is similar to our sun, showing that planetary systems like ours can form elsewhere. WASP 96b's watery atmosphere helps us understand how water and planets form, even in extreme places. Let's be clear, WASP 96b is not habitable. With scorching temperatures and a hydrogen-rich atmosphere, it's a world of extremes. No surface, no liquid water, just superheated steam. The excitement isn't about life here, but what it means for the galaxy. Finding water so easily on one of Webb's first targets suggests water is common in planetary formation. If a hot Jupiter has water, a cooler, rocky planet in the same system might too. The discovery is a signpost water worlds and Earth-like planets may be common. While WASP 96b is inhospitable, it increases the odds of finding a habitable world elsewhere. Understanding its atmosphere prepares us for studying true Earth-like candidates. We're learning to read the weather on alien worlds, a crucial step in our search for life. Finding water is just the first step in this incredible journey. It suggests the potential for habitability, but it doesn't guarantee life. The next challenge, searching for biosignatures, those telltale signs that could indicate the presence of living organisms on these distant worlds. Chemical fingerprints of life, unique combinations of molecules that are produced by living processes. On Earth, oxygen is a powerful biosignature, a direct result of photosynthetic life, constantly replenished by living things, ensuring its abundance in our atmosphere. Webb can search for combinations of gases, analyzing the light that passes through exoplanet atmospheres. Like oxygen and methane, gases that, when found together, could strongly suggest biological activity. That are hard to explain without life, combinations that defy simple geological or chemical explanations. This is difficult work, requiring meticulous analysis and careful consideration of all possibilities. Planets are complex and non-biological processes can mimic life signals, creating false positives that must be carefully ruled out. Scientists must rule out all other explanations, exhaustively investigating every potential source of a signal, before considering biology, ensuring that the evidence is truly compelling. The search for biosignatures will require a global effort, Webb and future observatories working together, pooling their resources and expertise. Ground-based telescopes and new space missions, each contributing unique perspectives and capabilities, will help build a complete picture, providing a more comprehensive understanding of exoplanet environments. We're entering an era of collaborative astronomy, where international teams work together, piecing together the story of distant worlds, unraveling the mysteries of their atmospheres and surfaces. A single biosignature might be ambiguous, open to multiple interpretations and requiring further investigation. But a suite of them on a habitable planet would be revolutionary, a compelling case for the existence of life beyond Earth. The hunt is on, and the stakes are incredibly high. For the chemical signs of life, those elusive indicators that could change everything. Each discovery brings us closer, step by step, to answering the ultimate question: are we alone in the universe? The search is painstaking, demanding countless hours of observation and analysis, but the potential reward is nothing less than a profound shift in our understanding of our place in the universe, changing humanity's place in the cosmos, forever altering our perspective on life itself. We are on the threshold of a new era, an era of unprecedented discovery and exploration. The James Webb Space Telescope is more than Hubble's successor. It's a new way of seeing the universe. Its infrared vision reveals what's been hidden: water on exoplanets, the birth of stars, the history of our solar system. Webb studies icy moons like Europa and Enceladus, searching for signs of habitability. It analyzes Mars, asteroids, and distant Kuiper Belt objects, deepening our understanding of our own origins. Looking farther, Webb is a time machine, capturing light from the first stars and galaxies. It peers through cosmic dust, revealing the universe's earliest moments. For centuries, we knew only our solar system. Now planets are everywhere. With Webb, we're moving from finding planets to truly knowing them. Every spectrum is a new piece of the universe's grand puzzle. The discovery of water on a distant exoplanet touches our deepest question: are we alone? For all of history, Earth was our only data point. Now, we know the building blocks of life are common. This transforms the search for life from philosophy to science. The universe feels less empty, more like a cosmic neighborhood filled with possibilities. Earth remains precious, but we now see it in a new cosmic context. Finding water vapor isn't finding life, but it's a critical milestone. It gives us hope and a reason to keep searching. We are the first generation with the tools to take real steps in this quest. The search for life is a multi-generational journey. Whether life is common or rare, the answer will reshape our understanding of ourselves. The universe invites us to explore, and with Webb,